Hi, welcome to Math 331 problem solving. I think this is lecture 31. If not, I'll fix that later. So I've got a couple of problems that I found interesting that I'd be happy to discuss. Are there any problems that people particularly enjoyed? Okay. If not, I will then mention one or two. I like, yes.
Can I ask for one?
Sure. Is it 210B1 by any chance?
No.
Are you sure it's not 210B1?
Actually, I think it is 210.
Okay. And after we do 210B1, what was the next one you were thinking of?
Number 5.
Okay. You waited just like half a second too long. All right. All right, so let's start with 210B1. So the question is, are there A1, A2, dot, 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 and R such that for all positive integer m, we have A1 to the m plus A2 to the m equals m. All right. So when you see this, what are your initial thoughts? I want a sequence of real numbers such that the sum of the mth powers is equal to m for every m. Do you think this is possible? No. Okay, why not? Yes.
Well, as m gets larger, right, the sequence has to get larger, but if you want the sequence to like converge, right, then the terms have to eventually get less than 1, which means that they're going to get smaller as m get larger.
Okay,
so that means that you need at least one term greater than 1 to like increase as m is increasing, so that
right, so if every term was less than 1 in absolute value, when we take the mth power, we're going to be making things smaller.
Right.
Now, of course, there could be issues with signs, because remember, we're not saying that these are all positive numbers. So what should we consider? Because the sign issue could make it a little bit challenging.
even powers.
Yeah, even powers. Study m even. Let's let bk equal ak squared. And then you would be studying just even, so then you would just be studying positive, or like some of them could be 0. If one of the a's is 0, however, we can just drop it. So we might as well assume all the numbers are positive now. And again, it's this thought process of trying to make some simplifications. That if any of the numbers were 0, we can just remove them because they will have no impact. And then we have issues with cancellation of sign. Well, if we look at just the even powers, then we no longer have to worry about cancellation due to sign. And now your argument that it has to converge is really going to play. So when we look at m equals 2, we get a1 squared plus a2 squared equals 2. How many of the a's could be at least 1? It is possible to have 2 a's equal to 1. So, but if that's the case, then everything else has to be 0. So either exactly 2 ak's are 1 less 0, or at most 1 ak is 1. So as soon as we do this, now we know that when we take higher powers, the terms are going to be getting smaller. And yet the sum is supposed to be increasing. So is this enough to prove it? That there is no such sequence? If we now look at m equals 4, we get a1 to the 4th plus a2 to the 4th plus dot 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 equals 4. And everything in here is going to be strictly less than, a3 squared plus a4 squared.
Well, I guess the idea is that you could have like a1 greater than 1.
So you could now have a1 greater than 1. So if we had two that were exactly 1, this would be enough to finish the proof. So if two of them are exactly 1, then we're done. We know a1 is at most 2. Well, actually, a1 is at most square root of 2. So if we had square root of 2 to the 4th power, that would be 4. So, all right, so maybe we are still alive at m equals 4. But maybe by the time we get up to m equals 6 or 8 or 10, this might be enough to finish the proof. But I like this idea of trying to break it into cases. What do we know? What's dangerous? The danger is the negative signs, is that things could be canceling. Well, we can ignore that. And now we can start to use the fact that because the series converges, we have the terms must be getting smaller. So when you take higher powers, it's going to be smaller. The challenge, of course, is if we have a number that's greater than 1. Then when we take a higher power, it gets bigger. But there can't be many of them. There's at most 2. So this immediately eliminates the case when there's exactly 2. Now we have the case of there being exactly 1. If there are none of them, then we're done. So we just have to worry about what if a1 is between 1 and 4? I'm sorry, a1 is between 1 and square root of 2. Well, we should be okay if we start looking at a high enough power. Or maybe not. This side is growing slowly. It's growing like m. So if we have a1 is maybe close to square root of 2, that could be large enough for quite a while. So we have to do some work based on what the value of a1 is. Yes?
So if a1 is greater than 1, then at some point it's growing like greater than linearly. Right?
So if a1 is greater than 1, now we have trouble. So we can break it up into if a1 equals 1, we're okay. If a1 is greater than 1, then we have exponential growth. And that's only polynomial growth here. So if a1 is greater than 1, eventually a1 to the m is going to kill the m. And then that would finish the proof. And then you just want to write this up carefully and clearly. There is, I think, another approach one could do for this problem. It's just a cute inequality to be aware of, or a cute idea to be aware of. So before I do that, any other questions on this approach? I really like the idea of trying to analyze it and take stock of what are the issues. And the issue is the negativity, yes.
Can you just say if a1 is greater than 1, then it's exponential and m is linear, and they'll take that? You don't have to prove that at some point the derivative.
When you give me your write-up of the Putnam for me to grade, I will accept that. I would have to believe on the Putnam that if you've got all the other arguments for the problem correct, and you just say that this is going exponentially fast, you can even say by L'Hopital's rule, something like that, you should be fine. If not, I know this is being recorded, then the Putnam scores mean nothing. If you have to go to that level of detail and proof. But I think you can just say, since the base is greater than 1, it's going exponentially fast. Exponentials beat polynomials. So here's one other fact we know. a1 squared plus a2 squared equals 2. Right? If we square both sides, we get 4. What do you get when you square this? So we're going to have a1 to the 4th plus a2 to the 4th right? Because when you square it, each one is going to hit itself, and then you'll have the cross terms.
That necessarily has to be less than 0.
Right. Plus cross terms equals 4, but that equals 4. And we're assuming that all the terms are positive. Because if any of the terms were 0, we could just ignore. So we've got to be a little bit careful. It never says that the infinite sequence of real numbers has to be non-zero. So as soon as there are 2 terms, there's a cross term. Right? If at least 2 terms are non-zero, there's a cross term. So the only case we then have to worry about is the case where the sequence has 1 term. And then we need a1 to the m to equal m for all m. Okay? Exists if at least 2 non-zero a's. If only a1 does not equal 0, it's trivial. So this is just to really warn you about how careful you have to be. It doesn't say in the problem that the sequence of numbers has to be non-zero. If you only had finitely many terms that were 0, or if you even had infinitely many terms that were 0 but had infinitely many terms that weren't 0, then you can just remove all of those. The only time it really matters or becomes interesting is if there are only finitely many terms that are non-zero. So I think this is the cleanest proof, is looking at the special case m equals 2 and squaring it. And then if there's a cross term, we're done. And then we don't have to worry about, do they know that exponential functions grow faster than polynomial functions? It's extremely elementary. The only thing we need to worry about is that there is a cross term. Well, the only way there's not a cross term is if we only have 1 term, and that's not so bad. So the reason I really liked this problem, and I was so glad that you were willing to change to 2010 V1. I knew it was. And that's what delayed you coming here today, just thinking about this problem. Sorry. It was so nice teaching here while it lasted. So what I like about this is there's a lot of different ways of solving this problem, but I think if you look at it the right way, you see the aha moment. And I think just squaring and just looking at m equals 2 and m equals 4, and you just see how elegant that is. You now don't have to use the calculus fact that the exponential function grows faster than the polynomial function. And that makes it a more elementary proof. And this is what you should remember. There are these tricks. There are these ways to look at these problems. Okay. What was your second favorite problem?
Number 5 on the first page.
Okay. Oh, yes, that's a fun one. So it's kind of like a continued fraction lurking in the background. So this is 1995. And you are told to find the 8th root of 2017 minus 1 over
2207.
Oh, sorry.
It's a Putnam problem in the future.
That's right. So actually, as a nice exercise, you can calculate with high probability what level of great-great-great-great-grandchildren of yours will be taking the Putnam in 2207. And then you can have them prepared. I remember in high school, I was doing math competitions, and my school never really prepared. If we were lucky, we would look at a few problems on the bus ride over. Our rival town had an entire class devoted to it. And I remember one year as we were riding over, one of the problems we looked at, they reused. And you didn't have to show your work. We all laughed, we all voted for, and we all moved on to the next problem. There's a huge advantage to reviewing problems, not just if they happen to use them again, but you start to see which methods the proposals like. This is why it's actually good to have people rotating off problem committees like this. So normally you only serve a couple of years on the committee. And I've actually had some friends who have served on the Putnam committee, which is a very interesting experience. All right, so they want 2207 minus 1 over 2207 minus 1 over 2207, etc., etc., etc. And I think they want you to evaluate it into a nice form, a plus b root c over d, where a, b, c, and d are integers. So they want this like a plus b square roots of c over d. That is a huge hint right there. They're telling you that you can express it with 4 integers and a square root. And we start off with an 8th root. All right. Thoughts on how to attack this one? So did you have any thoughts, or just it looks like fun? When you look at this problem, is there, so I guess one of the big words, I'll try to write it like this. So try symmetry. Right? Whenever you see a problem, ask yourself, is there any symmetry in the problem which I can exploit, which I can use to my advantage? Yes?
I don't know. I started by writing A equals 20. What?
Don't use A because they want A to be there. So how about X?
X
Yes.
equals 2207 minus 1 over X.
Good. So if, I would say let X equal, 2207 minus 1 over 2207 minus 1 over 2207. So let's let X be that whole expression. And then you immediately get X equals 2207 minus 1 over X. Because this part over here is just X again. So what we get now is X to the 1/8 is equal to 2207 minus 1 over X. Wait a minute, okay, sorry.
I would multiply through by X.
So if I take the 8th power of this, I get X. Right? What's inside the here. So this we're calculating the 8th root of X, correct? So we have X to the 1 over 8. That's what we're calculating. So this is the 8th root of 2207 minus 1 over X. So if we take the 8th power of both sides, we get X equals 2207 minus 1 over X, which means if you multiply through by X, X squared equals 2207 minus 1, X minus 1. And so you get X squared minus 2207X plus 1 equals 0. And you have 2 roots. Are the roots both positive, negative, complex? What can you say just by looking at this? So the question is it interesting? Should I do the quadratic formula? Should I try to factor 2207? I want to write this. It's X minus R1, X minus R2. Could both roots be positive? Yeah, if both roots are positive, the product will be 1. It depends on how you want to look at it. I'm writing it as X minus R1. If one root was positive and one root was negative, I would have a negative sign here. So that can't be the case. If both roots were negative, then this cross term, so both roots are positive. So I know both roots are positive. So unfortunately, the problem now requires a little bit more work. I've got to solve this. And hopefully only one of the 2 roots will work. when we use the quadratic formula. Yes?
Well, it's gonna be the bigger one, right?
What if both of the roots,
Well, their product is 1,
their product is 1?
so
Good, so since we know their product is 1,
and then x we know is greater than 2206.
with a little bit of work, I'm sure you can prove that.
Yeah.
Let's say x is greater than 5. You know, I'm quite comfortable on something like that. So we know that x has to be greater than 5, and that allows us to eliminate one of the roots. And so now when we do negative b plus or minus, it's going to be the plus that matters. So how come we got an extra root? You know, why are we getting 2 roots when only 1 root works? Alright, let's say we want to solve x equals negative 1. Okay, I realize that this is not a hard equation to solve for x. Okay, let's square both sides until we get x squared equals 1. So we get x squared minus 1 equals 0. So we get x minus 1 times x plus 1 equals 0. So we get x equals 1 or negative 1. So the solutions to x equals negative 1 are 1 or negative 1.
Since you were going by an even power, to split, there can be 2 solutions?
So a polynomial of degree 2 will have 2 solutions.
There are 2 equations such that taking the 8th power will yield the...
But I'm saying right over here, what went wrong? Why do we have an extra solution? Yeah, when you square, you can introduce an extra solution. If you start off with x equals negative 1, this is at the level of the prereq for the class. You should be able to find the solutions to this equation. Right? There's only one solution. But when I square it, I introduce an extra phantom root. Over here, when we multiply through by x, are we introducing an extra root? Where is this coming from? Well, we raised it to the 8th power over here. That's the real killer. It was that stuff there. So there could be, we're lucky that there aren't other solutions we need to worry about. So there's only 2 possible solutions here. It's going to be the larger root. Now you can just use the quadratic formula and just finish the job. So this is a nice problem. The fact that this is so symmetric, it's screaming at you to introduce a variable for that quantity and build that into your argument. A lot of times there are Putnam problems that involve integrating over some regions. And it turns out the integrand is often symmetric, maybe with respect to the midpoint of the interval. Or there's some kind of change of variables and one part changes into another. Or if you add something to it, it becomes nice. So I'll just make a couple of just general comments. How good are people with their trig integration?
4.
So let's integrate from 0 to 2 pi cosine squared x dx. Anybody remember the antiderivative of cosine squared? So cosine of 2x is cosine cosine minus sine sine. So that's cosine squared minus sine squared. Well, that's the same as 2 cosine squared of x minus 1, because sine squared is 1 minus cosine squared. So you get cosine squared of x is going to be 1/2 cosine of 2x plus a half, if I've done the algebra correctly. And now I can integrate this. You do not want to do this. But, here is a way to do it. I'm integrating cosine squared from 0 to 2 pi. What else could I have integrated from 0 to 2 pi? Be more powerful. What? Be more powerful. sine squared, right? This is the same as the integral from 0 to 2 pi of sine squared of x dx. So if I have to integrate cosine squared from 0 to 2 pi, it turns out that that is the same as half the integral from 0 to 2 pi of cosine squared x plus sine squared of x dx. And so this integrand was actually missing its complement. And when I put in the complementary part of it, it's now a very nice integration to do. We are now integrating from 0 to 2 pi the function 1 dx. I debated leaving it to you, but it's I'll just write pi. Oftentimes, complete integrals are nice, over the full cycle, or 0 to infinity, or negative infinity to infinity, and integration over just general regions are often hard. So for this one, and there's a lot of Putnam problems like this, if you find the corresponding piece, it's nice. There is a math riddle on my website that I'll talk about next. I just want to make sure, does anybody have any other questions on this? So I don't know if they will give you something like that, but if they give you an integral to evaluate, almost surely there's a nicer integral floating in the background that you should look at. Do a change of variable, add a piece that has the same value. How many of you remember hearing of something called Stokes' theorem or Green's theorem? If you want to have fun when you're teaching Calc 3 and you're doing line integrals, you give people line integrals before they've learned Green's theorem or Stokes' theorem. And you do it with things that have very nice curls. So as the professor, you can do the calculation very easily. In fact, what's typically the curl that you will choose? The dq dx minus dp dy. What would you like that to be as a professor? Even if you don't remember Green's theorem or Stokes' theorem, what's the one number you'd love that to be to integrate? Almost off by 1. There you go. 0, right? If I give you an integrand of 0, it's very easy to calculate what it is. And so what you can often do if you want to make sure that you have the right answer, you choose a function where you can use Green's theorem or Stokes' theorem to evaluate it. And then you can check and see if the calculation was done correctly. So look for missing pieces. So this is all coming from the symmetry embedded in this problem. So here is another one which I think I gave on my math illustration. Just want to make sure I do it correctly. Right. Oh shoot. No. No, I don't want that. Yeah. This is what I want. I want to solve x to the 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 x equals 2. So you've got to be careful as to what this means. So with exponents, it's always a little bit tricky. So if I give you x to the x, and I take x to that, and I take x to that. So just being very careful as to what I mean. So I'm writing this right after we've done this. So there should be some symmetry. Something should be screaming at you.
X squared equals 2.
X squared equals 2. So this whole thing over here is basically what you've started with. So that has to be 2. So therefore you get x squared equals 2. And now you can see why I slipped and started by writing root 2 to the root 2 to the root 2 to the root 2. I started with the answer. So now we're trying to solve x squared equals 2. All right, that's not bad. X equals root 2 or negative root 2. And we'll go with x equals root 2. Yes?
Sorry, can you explain why it's x squared?
Sure, because x to the 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 x equals 2. If I just forget about the first x over here, I've got x to the x, well that's the same expression.
Right.
So if you want, let y equal x to the x to the x. We know y equals 2. And we also know x to the y equals 2. Because we can just substitute.
Yeah.
Yep. There is a question you should ask if you are a mathematician when you see an expression like this. What question should you ask?
Can you do it infinitely often?
Yeah, can you do it infinitely? Does this actually converge? Does this make sense? For what values of x can you actually compute x to the x to the x to the x to the x? So I'll leave that as something for you to ponder. For what values of x can this be made meaningful? Did I show you the...
Is it any n to the 1 over n power?
Any, say that again?
Where x equals any n to the 1 over n?
Well, so...
Because then you have like the cancellation.
So what you're saying is, if we took the third root of 3, the fourth root of 4,
yeah.
So all of those numbers will actually be less than the square root of 2.
Right.
So maybe this will make sense for all values of x less than the square root of 2.
Oh,
so,
as in like equivalent to 2 is...
Oh, wait, so...
Oh, I was thinking equivalent to n.
Yes. So the more general question is, if we want this to equal n, what will work? And then we would get x to the n equals n, and then we get x equals n to the 1 over n. Right. So my question was just, for what values of x does that infinite tower exist? So can you prove that it will always converge if x is between, say, 1 and root 2? And so I'll leave that as an exercise for you to think about, for what values will this make sense? It's not initially clear that just because I've written this down, that the expression x to the x to the... But if we want to just play games formally, sure. Did I show you the formal playing with integral signs? I can't remember if I showed you this one. So my physics mentor showed me this when I was a student. Define integral of f to be the integral from 0 to x of f of t dt. Solve integral of f equals f of x minus 1. Did we ever do this in class?
No.
Oh, this is worth doing. Okay. Did anybody bring their engineering hat today, or even better, an economics hat? So do you know what these hats allow you to do?
Make tons of assumptions.
Change integrals?
Yeah, just do whatever you need to do without worrying about convergence, without worrying about justification. It basically just means you know a mathematician who can help you out and check at the end. All right, so I'm going to solve this. Now, if you think about it, the integral of e to the t dt from 0 to x is going to just be e to the x minus 1. So it looks like, here's one solution, the exponential function. I will show that that is the only solution by doing a whole string of illegal operations, which can all be justified if you take enough math. So I was shown this right before Thanksgiving because my professor, even though he was British, wanted us to have something to talk about at the Thanksgiving table. Hi. So this is so it's the same as 1 minus the integral of f equals f. I've just moved things over to the other side. No big deal. So this is 1 minus integral acting on f. Oh, no, sorry, no, I want to do it the other way, sorry. I want to do it as f minus the integral of f equals 1. So this is the same as 1 minus the integral acting on f equals 1. So now we apply the operator 1 minus integral inverse to both sides. And we get 1 minus integral inverse acting on 1 minus integral acting on f is 1 minus integral inverse acting on 1. Oh, no, we haven't even reached the divine inspiration yet. All right, so 1 minus integral inverse applied to 1 minus integral is clearly just going to be the identity operator. What's 1 minus integral inverse?
1 over 1 minus.
1 minus derivative.
No! Now, even economists have standards. You have to sometimes squint, but what's 1 minus integral inverse? You were close with 1 divided by 1 minus integral, but what's 1 divided by 1 minus integral? So, I mean, if I gave you 1 over 1 minus integral, how would you expand this?
Multiply 1 plus integral
No.
over 1 plus integral.
You've got 1 over 1 minus integral. How would you expand this? What does this look like? 1 over 1 minus...
Oh, geometric series.
Yeah, it's a geometric series. Where r equals integral. So it's just 1 plus integral plus integral integral plus integral 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 acting on 1. I told you we hadn't reached the point where we were asking for God's help yet. Now we have. So we get f of x. Now, what's 1 acting on 1? 1. Now we have integral acting on 1. So integral of f is just the integral from 0 to x of f of t. So what do we get when we integrate 1 from 0 to x? We get x. Now we have integral applied to 1. The first integral applied to 1 gives us the function x. So now we apply integral to x. We integrate the function t from 0 to x. We get not 1/2 x squared, close. I don't want to say 1/2. What should I say? 1 over 2 factorial. Plus x squared over 2 factorial. So now we have integral. The first two integrals give me the function x squared over 2 factorial. So I now integrate t squared over 2 factorial again. T cubed over 3 factorial. So I get x cubed over 3 factorial. And there's your exponential function. And this can all be justified. So a really good physicist or economist knows how to justify things, or has a really good sense of what things their friends can justify. So you need to define what it means to take the inverse of an operator. You need to define or understand when can you actually have a series expansion for the inverse of the operator. You need to introduce something called the operator norm. And you have to look at the space of functions where this is applicable. This can be justified. So this is one of my favorite arguments that I have seen. And again, there is good math floating in the background. All right, we've got 10 minutes left. Given that we don't have a huge amount of time, I'd like to choose a specific problem, and we'll save other problems for Friday. This is 2009 A1, and then if there's time, we'll do 2009 B1. 2009 was actually a nice year for the Putnam. They have punished the people, I think, who wrote those problems. So I think B1 is a little bit easier than A1 if you can look at it the right way. The hardest part with A1 is not to make additional assumptions. So this is 2009 A1. So f of A plus f of B plus f of C plus f of D equals 0 whenever A, B, C, D corners of a square. And what they ask you to prove is f of P identically 0? So take any point P and choose points A, B, C, and D. What do we know about f of A plus f of B plus f of C plus f of D? If this is a square. 0. So now just shrink the square inward. Right? So just take smaller and smaller squares centered about the point P. What does f of B approach as we take small and small squares? P. It approaches, the point B approaches P, so we get, if you want, you can even put ends on them. we get f of an goes to f of p, f of bn, f of cn, f of dn, they all go to p. So since the sum is 0, what does f of p have to go be?
0.
Has to be 0. So f of an plus f of dn has to go to 4 f of p. And since this goes to 0, that means this has to go to 0. Is this a proof? So I tell you that whenever you have a square, f of a, f of b, f of c, f of d, that sum equals 0. F is a real valued function on the plane. Does it follow that f of p is identically 0? So we chose an arbitrary point. We took a sequence of squares squishing in. Is this sufficient to prove that f of p is identically 0?
You consider a 0 area square?
Yes.
Still be a square?
Well, because what I can do is, I can take an arbitrarily small square. And if f of p were not 0 by continuity, there'd be a small neighborhood around p where the function is positive or negative. So without loss of generality, if f of p is not 0, we can always renormalize and make f of p equal to 1. And then we can choose a very small delta so that if we're within delta of p, then the value of f will be within epsilon of 1. So by continuity, we're done. What's the problem?
Didn't say f was continuous?
Yeah, it never said f was continuous. So this is what happens when you assume. Okay? It is very, very easy to make assumptions and not even be aware that you're doing it. So for this problem, it never says f is a continuous function. F is a real value function. Think of it, if you want, as that time when we tapped the wand on the board and all the points that were rational distances from the tap survived and all the other points were destroyed. So we don't have continuity at all. So the question is, what credit would the Putnam people give to this proof? What is the maximum possible in your mind?
None.
I would say at most 1, possibly none. Because this proves it in the special case of continuous functions. Well, most functions aren't continuous. So sadly, that argument is invalid. Now, it wasn't a bad idea to take a point P in the center and try to look at what's going on at some other points. And so the question is, what points do we want to look at? And so I can take my points as before. And I know if I call this A, B, C, and D, I have a giant square here. So f of A plus B plus C plus D is going to be 0. Can you think of any other squares that we have, or almost have? Yes. I'm sorry?
Wait, why is it almost?
I don't think we have any other squares right now.
Oh, well.
You can make a side out of P to A.
Okay, so where do you want to put points?
I think we could like P, A, B, and some other.
So P, A, B, so we have these as 3 points. Where should we put the fourth? Has to be here. Has to be here, has to be here, has to be here. And draw pictures. And for this problem, we want to get squares. This is like when I gave you the proof through dimensional analysis of Pythagoras. We dropped an altitude to get more right triangles because we wanted right triangles. Here we want squares for this problem. So if I put in these extra points, I get some more squares. And so now we'll call this maybe alpha, beta, gamma, and delta. So we know f of a plus b plus c plus d is 0. We know f of alpha plus beta plus gamma plus delta is 0. And so if we just sum all the squares, how many times do we get the point P? 4 times. So we get 4 f of P. And then how many times do we get A, B, C, and D?
2 times for each.
I'm sorry?
2 times for each one.
Let's see. A is in 2 squares here.
3 times.
3 times. So we get plus 3 times f of A plus f of D. And now what about alpha, beta, gamma, and delta? Each one we get once. Twice.
You have the big one.
We have the big one.
Oh, I see.
Although actually we don't need that big one. We can have it if we want. It doesn't matter. Right? So f of alpha plus f of delta. And that equals 0. And we know what's inside here equals 0, and what's inside here equals 0. So 4f of p has to be 0. So the question is, was it worthwhile to spend a little bit of time and add this assumption that f is continuous? If so, you have to remember that you made the assumption f is continuous, and the problem is supposed to be true for all functions. Sometimes it's not bad to put in an extra assumption, just try to build some intuition and see. The danger with that is your proof could fundamentally use that continuity, which you don't have in general. Yes?
If you're actually writing out the solution for the Putnam, what extra details would you have?
I mean, I would basically say I have the following squares. I have the square, A, B, C, D. I have the square A, alpha, beta, P, etc., etc., etc. I would enumerate all the squares. Just because it takes so little time to do this, it's worth doing it and not risking losing some points. For me, when you write things up, it's pretty clear. I know what's going on as soon as I see this. So there is a danger of being misled from special cases. Now, they ask you to prove, or they say, does it follow that f of p is 0 for all points p in the plane? Well, if you can find even one function where it's not always 0, then you're done. So maybe it's not a bad idea to assume that the function is continuous and try to find a counterexample from there. Then if that fails, then go through and try something else. All right, so this is a good place to stop.